All right, continuing where we left off, we're going to discuss what's called the two-body problem. Um, and so two-body problem just means we've got two bodies, which is usually going to be a more massive body like the Earth or another planet, and say a satellite or a rocket. And we're interested in the trajectories or the motion of these two bodies relative to each other. And this is, the most common case. If you go study orbital mechanics in more detail, you can look at multi-bodies, and it's really the same physics, but in this two-body case, again, which is the most common, we can simplify some things and come up with some equations. So we can actually, I'm not going to derive it here, but it's discussed more in the textbook. We can derive an equation for the position of this particle. So here, or sorry, not particle, this object, R, its position R, which is not a constant necessarily, it could be moving around. And it's going to depend on a few things. One of them is the angular momentum. So the angular momentum is going to be conserved because there are no external torques on the system, right? It's just the interaction between these two bodies. There's no other external torques. Then we know the angular momentum must be constant. Okay, and so angular momentum is going to be I times omega, so we could write it mr squared. That's the moment of inertia of that body, and its rotational velocity is going to be theta dot. Right, so let's call this theta. Let me redraw that here. So here's big M, little m, r, theta. Theta dot is omega, right? That's how much it's rotating. And we're actually going to use the angular momentum per unit mass. So that's just r squared theta dot. So angular momentum per unit mass. That's also going to be conserved. That's just the form that's going to show up in this equation. All right, and we could also, well, we'll just leave it at that for now. So the two-body problem, the equation we get with this orbit equation, we can derive it from an energy perspective, as I mentioned. That's shown in the textbook. It's of this form: R is equal to h squared divided by mu, all over 1 plus e times the cosine of theta minus theta naught. Okay, h we just talked about, that's our angular momentum per unit mass. Mu, remember we discussed this last time, it's just the product of g times m. We often like to combine them because we use them a bunch, and so we want to keep multiplying two constants. E is called the eccentricity. And it's also given by a formula. It looks like follows: 1 plus 2 h over mu squared times difference in energy per mass. So T is the kinetic energy, U is the potential energy. The details of this equation is not important. I'm just writing here to be complete. Theta. So this is describing basically R, my position, as a function of theta. So as this goes around, where is this going to go? Is it in a circle? Is it ellipse? Some other weird shape? How does it go? And it's going to depend on these other parameters, the angular momentum I have. Basically, things that will occur at the burnout once I finish, injecting a force through a propulsion, through a rocket or whatever, and I stop, and now all that's governing my motion is gravity, and this equation will describe what's going to happen. So the insight, though, that we really want to focus on here, not the equation per se, is that this equation is exactly the same as a conic section described in polar coordinates. So, you remember way back to geometry or some earlier math classes. So this describes like an ellipse, hyperbola, things like that. And so there really are actually only a few possibilities for the motion of these objects in a two-body problem. Okay, and so here's an example. This is, say, one object, the Earth. Here's an object, a satellite. And our first possible motion is an ellipse. And this is going to occur if the kinetic energy of my satellite or my object is less than the potential energy. So that's this term here. Kinetic energy, potential energy. That determines my eccentricity, and that determines the type of orbit I can get. Now, I need this exact equation so I can figure out exactly how big that ellipse is, what the angle of it is, and so on. But to just kind of understand the nature of it, which is what we're focusing on, anytime the kinetic energy is less than the potential energy, we will have an elliptical orbit. And a circle is an ellipse, right? That's the extreme end of the ellipse. That's the eccentricity goes all the way down to 0. So this is an eccentricity between 0 and 1. And this should make some intuitive sense, right? That if my kinetic energy is less than that gravitational potential energy, I'm not escaping that potential energy. If it's less than it, then I'm going to have some bounded trajectory. I'm not going to be able to escape that potential energy from gravity. On the other end, if the kinetic energy exceeds the potential energy, I will have a hyperbola, right? So this is never coming back. Once I pass by this body, if I have a certain velocity, I'm never going to return. I'm just going to go off, infinitely far away. And the limiting case between those two is a parabola. That's there's nothing really special per se. It's just the boundary between the two that also escapes. In fact, the parabola, if you look at the velocity, that's also another way to define that escape velocity. It's the velocity that's going to get me on this parabolic orbit, right? So where I just barely get away from the gravitational pull. If I have more, well, then I go even further. It's a hyperbola. I'm going to get to infinitely far away out of that gravitational pull with excess energy to spare. And if I have less than it, then this could be a really big ellipse, but I'm eventually going to come back. And that's it. Those are the only possibilities for this two-body problem. I'm either going to have an ellipse, and the parabola is really just kind of that limited case. So it's essentially going to be an ellipse or a hyperbola. So that's kind of the main conceptual takeaway. If you wanted to work this out, we don't have, unfortunately, we don't have a homework problem to do just because of time, so we're not going to do it. But I'm just going to walk you through how this would normally work. So say I have a satellite or whatever rocket, and I just finished, expending all my propulsion, and now I want to see what's going to happen. I want to understand behavior, or more directly, I want to know how I should expend my propulsion at what angle so that I can get the orbit that I want. So here I am at some distance away from the body, some radius, and I've got some given latitude. This is just defining my current position. And then this velocity vector defines my current trajectory. So that's where my velocity is at that instantaneous time. And beta here, this is just some angle from the local horizon. So this would be a right angle. So this is just tell me what my angle is offset from that. So we said that h is r squared theta dot. By definition, we could also write that as r times v theta, right? Because r omega dot, that's just the perpendicular component of my velocity. Or in this case, in these variables I've used, this is r, and v theta here is this component of VB. Okay, so that's VB times cosine of beta B. Okay, so these are all parameters I would know at the instant in time when I've finished burning my propulsion, my propellant. I know my position, my latitude, my trajectory, my inclination there, and I just plug that in. I can figure out what my angular momentum per unit mass is, and that's going to be conserved. That's not changing. I can calculate my eccentricity. 1 plus 2 is just writing that same equation again. These are all constants I know. T minus u over m. So T again is 1/2 mv squared. I know my velocity. That's just this 1/2 m times vb squared. And potential energy, that's that equation minus gmm over r. So I know how far away I am. So these are all things I know. I can plug it in. I can compare to see if I'm on an elliptical orbit or a hyperbolic orbit. And the last part, to finish this equation here. So I know h, I know mu, I know e. I just need to figure out what theta naught is. So the way I'm going to do that is that I'm going to, so this equation describes my trajectory for all time going forward or backward if you wanted to reverse it, going forward. So I just need one condition. If I know 1r, then I can back solve this for what the theta naught has to be. that's just what we're going to do here. Just need one condition. So theta naught, I'm just solving that equation for theta naught. It's theta b minus the arc cosine. Again, these details aren't, you're not going to need these in the homework, but this is just to help you get some context here. So now these are all parameters I know. So what I'm doing is I'm taking this point where I know something. I know r and my theta at some point in time. So I can plug that into the equation to get what theta naught is. Now I have all the parameters I need. Oops. H, E, theta naught, mu. I have all the parameters I need to describe r and theta for the full orbit. So I can continue and plug in future values of theta, and see what happens as I go around. And most of the time, that's going to be an ellipse. That's the most common case by far, right? Is to find elliptical trajectory. So here's an example. This black circle, this is from the textbook, just an example. Created here, the black circle, this is Earth. And at some point in time, I know that I have a burnout speed of 9 kilometers per second, an altitude of 800 kilometers, latitude 30 degrees, and inclination angle 5 degrees. So I know when I burned out. From that information, I just run through these equations, and I propagate theta forward, going around this full ellipse here, and I can trace out exactly what my trajectory is going to be. So I'm going to know where I'm going to go. So if I want to achieve a certain trajectory, I want to reach a certain point, I can then figure out, what angle or what speed I need to achieve with my propellant to get me there. Okay, so that's kind of the more general case, but we're going to really focus on an ellipse because that's by far the most common scenario, and that's going to be a bit simpler. So here's an elliptical orbit. I've got a satellite moving in an ellipse around the Earth here. And we're going to have a point of closest approach, and that is called parapsis. More generally, if it's the Earth, we call it perigee. So I'm just going to write that. This is perigee. So that means that's the point of my orbit that is closest to Earth in this case. The furthest point away from a body in general is called apoapsis, but for the Earth, it's going to be apogee. Okay, so those are the closest and furthest points of approach. And again, I'm not going to derive this, but this is in the text if you want to see it. My velocity at any point in this ellipse is going to be given by the square root of g times m, which we've also called mu, 2 over r minus 1 over a, where a is my semi-major axis. So this is a. All right, so for an ellipse, I don't have a radius. I have what's called the semi-minor axis. That would be the smaller distance from the center to an edge, the smallest distance, and then a is the biggest distance. That's called the semi-major axis. So that's just a constant for the ellipse. So from my elliptical shape, if I know what that shape is, I plug in a, these are just constants. I can calculate my velocity at any point in that radius. From conservation of angular momentum, I also know, for example, that v theta 1 r1 equals v theta 2 r2. That can come in handy sometimes. That's mostly handy at perigee and apogee because I'm going to be moving at a right angle. At these other distances, it's a little less convenient because we have to work out the tangential component, but still can be useful. All right, so question, where on this orbit will I be going the fastest and where will we be going the slowest? Well, from conservation of angular momentum, so I just kind of wrote here, when my distance is smallest, then my velocity is going to be largest, right? Because I have to conserve angular momentum. So I'm going to be going fastest here at perigee, slowest here at apogee, and that probably makes some intuitive sense, right? I slow down here, I speed up on this end at perigee, just because of conservation of angular momentum. Notice also that if we plugged in, if this was a circle, then a would be equal to the radius. So I'd get 2 over r minus 1 over r. That would just reduce to 1 over r. So I'd have v as the square root of gm over r. If you go back to last time, it's exactly what we derived for the velocity needed to maintain a circular orbit. So that's good, that's consistent. Okay, so now we're going to use this to do a transfer. This is going to be the last thing we're going to talk about. We're going to do a transfer between two orbits. So let's say I'm in an orbit, I've got a satellite and I'm moving it around. It's in an orbit around the Earth as so, but I want it to orbit at some further distance, okay? So that initial orbit, we call that the parking orbit, where it started, it's parked in parking orbit, and here's my target orbit. This is where I'd like to go. And so the question is, if I want to get from one orbit to the other, how shall I do that? And you can see the direction I'm going. I still want to maintain the same clockwise orientation, and these are going to be in the same plane. So I'd like you to brainstorm, think about that for a minute or two. And there's not just one answer, but think about what you might do, what type of trajectory you might suggest to transfer from one orbit to the next. So a common one is what's called the Hohmann transfer here. This is a minimum energy transfer. It's not the fastest, but it's the one that takes the least energy. So that's often what we care about. And it's one that is going to form an ellipse. So it's an elliptical. Basically what we do is we're going to transfer to an elliptical orbit. And draw it like this, where the ellipse is just tangent to the outer orbit and just tangent here to this inner orbit. And so here's the dashed line, what it would look like if we were into that full ellipse. So what happens is I'm coming around this circle here, and at this point I'm going to accelerate. I'm going to expend thrust for my rocket, right, to exert some delta V, and that's going to push me into a new orbit. And that new orbit I get pushed into is this ellipse. And so now I'm in this elliptical orbit because I've added some energy. And if I did nothing, if I just stopped at that point, I'd just stay in this elliptical orbit and I just keep going around the Earth like this. But what I'm going to do is when I come around here, I'm going to then fire my rockets again with another delta V that we were going to calculate. And that's going to push me into this circular orbit. And then I'm done. I'm into this new circular orbit, and then I can just stay there. And I'll just keep going around in the circle. We know from what we just talked about last time that, remember the velocity, and this time, right? Remember for a circle, the velocity is going to be gm over r. For a circle, right? This reduces to gm over r. So we know that it takes less velocity to maintain this orbit than this one because r is bigger, right? So we're going to be moving faster here. This orbit is slower. So it seems somewhat counterintuitive. I said we had to expend thrust both times. We had to speed up here and we had to speed up here. But how is that possible? If I'm moving faster here, I'm moving slower here, why would I speed up both times? Think about that for a second. So, well, it may seem counterintuitive at first. Remember, we have to expend energy here. So we have to expend energy to get into this orbit here. And the reason we have to speed up again is because, as we just talked about, we conserve angular momentum. So this is actually our fastest approach on the ellipse. So by the time we get to the other side of the ellipse, we actually slow down. And it's such that to get back into the circular orbit, we have to speed up again. So we speed up both times. So the way we could calculate this, first, let's say this is orbit 1. So we can calculate delta V1, okay? So we know the velocity, let's say this is the velocity for the ellipse, that's my final, minus at 1, let's say, minus V circle 1. So I'm trying to figure out how much velocity do I need to change by. So my goal is to get into this elliptical orbit, and my starting point, so this final minus initial, my starting point is this circle. Well, we know what velocity of the ellipse is, right? That's just this equation here, and we're going to be here at perigee. So we know that distance, so we can plug that in. We can calculate how much velocity I need to have to get into that ellipse. We also know what the velocity is for that circle. That's just going to be the same thing except for circle, gm over r, square root of gm over r. So I know what that is as well. So these are both equations that I know, so I can calculate what delta V is. If I know what delta V is, we go back to our rocket equation. I can figure out how much propellant do I need, or how much propellant do I need to burn to make that happen. Okay, and of course, burning the propellant is not instantaneous, but it's a good approximation for the size of these. The time that we burn propellant is so small compared to the time it takes to traverse here that for this initial estimate, we can think of it as instantaneous delta V. Similarly, we do the same thing. We're going to calculate delta V2. How much do we need to expand to get into the second orbit? And so my final is going to be what's the velocity I need for the large circle? So final minus initial, and then that's going to be my ellipse. And the ellipse, these are not the same, right? Because this is the velocity of the ellipse all the way over here at apogee, right? So same kind of formulas. I'm just using this formula again for an ellipse or for a circle. And I'm just taking final minus initial so I can calculate what's my velocity changes needed to get into this orbit, what's my velocity change needed to get into this next orbit, and then I can calculate from the rocket equation how much propellant I burn here and how much propellant I burn here. And I could add those together and figure out how much total propellant I would need, for example, to complete this mission. If we wanted to reverse this, like say we wanted to go from the big orbit to the small orbit, it's very much the same kind of calculations. The delta V will be the same, exactly the same, except for we'd have to fire rockets in the opposite direction to slow the spacecraft down in both cases, to slow it down to get in here and then slow it down again to get into that circular orbit. So, I mean, this is the same kind of process. We're just going to look as if we were going around different orbits and around Earth, which is a common scenario. This also is a similar idea that can be used for interplanetary transfer if I want to get from, say, orbiting around the Earth to getting around Mars or whatever. The planets are not actually exactly coplanar, like is defined in this picture, but they're pretty close. And there are generalizations of this approach that we could use. But it's a bit more difficult with interplanetary transfer because it's not just that we have to get there. In this scenario, all we have to do is get from this orbit to this orbit, and that's all we have to worry about. But if we wanted to get to interplanetary transfer, I got to get from one orbit to another orbit that gets me to Mars, but I also have to get there at the time when Mars is there, right? It doesn't do any good if I get out to the distance of where Mars is at, but Mars is at a different place in its own orbit. So we have to arrive at the right moment. And it's not that that's hard from an equation standpoint, it just means it's trickier from logistics. We just don't have a big window. So for example, from going from Earth to Mars, if you want to do a Hohmann transfer, it's about every 2 years, like 2.13 years or something, is the window, or is how often you could do that. So this is why, for example, going to Mars is a bigger deal. We need to be sure that we have all things that we need, right? If there's some incident and you got to bring some people back for some medical care or whatever, you can't just do that. You miss a window, you could be waiting, a couple of years potentially before that window comes back around. So you have to be pretty self-sufficient. Okay, so that concludes this lecture and the lectures for our class. And so I hope you have a good one. I hope you've enjoyed learning some about flight. And of course, we're really just kind of scratching the surface here. We've introduced a broad range of topics that are relevant to aerospace engineers, but each of these topics has more depth, and I wish you the best on your continued journey to continue learning more about these fascinating topics. Have a good day, everyone.